Hello and welcome again. In today's episode, we shall learn about fundamental principles of counting and their applications. This script shall also help us learn to solve several counting problems through the fundamental principles of counting and the concept of permutation and combinations. I'm Nilofer Zargam, teaching in the Center for Management Studies, Jamia Millia Islamia University. Today we shall learn the application of fundamental principles of counting and different types of permutation and combinations in counting the objects. If an event can occur in m different ways, and if for each occurrence of the first event, a second event can occur in n different ways, then two events in succession can occur in mn different ways. The above principle can be extended for any finite number of occurrences of event and may be stated as: if an event can occur in m different ways, a second event can occur independently in n different ways, and a third event can occur independently in p different ways, and so on, then the total number of ways of occurrence of all the events is given as m into n into p, and so on. This is called the multiplication principle. Let's take an example here. There are 30 boys and 21 girls in a class. In how many ways can one boy and one girl be selected to represent the class? So the solution here is there are 30 ways to select a boy student. For each of these ways, there are 21 ways to select a girl student. Therefore, by applying the multiplication principle, the required number of ways will be 30 into 21, that is equal to 630 ways. Let's take an example. How many number between 100 and 1000 can be formed with the digits 0, 1, 4, 3, 5 and 6? How many of them are even and how many are odd when repetition of digits is not allowed? The solution to this comes as: the number lying between 100 and 1000 consists of 3 digits. 100 place can be filled with any of the given digits except 0. Therefore, 100 place can be filled in 5 ways. Now, tens place can be filled with any of the remaining 5 digits, including 0. Thus, the unit place can be filled with any of the remaining 4 digits. Therefore, the total number of required numbers will be 5 into 5 into 4, that is equal to 100. Now, for odd numbers, units place can be filled with any of the digits 1, 3, 5. So, number of ways to fill the unit place is 3 here. Hundreds place can be filled with any of the remaining 3 digits except 0. Thus, the number of ways to fill 100 place are 4 here. Now, tens place can be filled in 4 ways by remaining 4 digits. Therefore, the required number of odd numbers here will be 3 into 4 into 4, that is equal to 48. Now, for even numbers, required number of even numbers will be total numbers minus the odd numbers. So, that is 100 minus 48, that gives you 52. If two events can occur independently in exactly m and n ways respectively, then either of the two events can occur in m plus n ways. This principle can be extended for occurrence of any finite number of events. That is, if 3 or more events can occur independently in exactly m, n, p and so on ways respectively, then either of these events can occur in m plus n plus p plus so on ways. For example, there are 30 boys and 21 girls in a class. In how many ways can one student be selected to represent the class here? So here the solution will be: there are 30 ways to select a boy student and there are 21 ways to select a girl student. Therefore, by addition principle, the required number of ways to select either a boy student or a girl student will be 30 plus 21, that is equal to 51 ways. Now let's see example number 2 here. A girl has 1 library card. In how many ways can she take a book out of 10 books on chemistry and 8 books on biology? The solution here is: number of ways to take a book on chemistry is 10. Number of ways to take a book on biology is 8. Therefore, the required number of ways to take either a book on chemistry or a book on a biology will be 10 plus 8. This is equal to 18, and this was a simple addition principle example. Now let's see example number 3 here. There are 15 red balls, 12 blue balls and 6 white balls to choose from. In how many ways can a boy choose 2 different balls? Solution to this is: a red ball can be selected in 15 ways and a blue ball can be selected in 12 ways. Therefore, the number of ways to select one red ball and one blue ball will be 15 into 12, that is 180 ways. Similarly, number of ways to choose one red and one white ball will be 15 into 6, that is equal to 90 ways. And number of ways to choose one blue and one white ball will be 12 into 6, that is 72 ways. Therefore, the required number of ways to select either one red ball and one blue ball, or number of ways to select one red and one white ball, or number of ways to select one blue and one white ball will be 180 plus 90 plus 72, that is equal to 342 ways. This is the product of first n natural numbers, and it is denoted by n factorial, and we read it as n factorial. N factorial is equal to n into n minus 1 into n minus 2 into n minus 3, so on, 3 into 2 into 1. Therefore, we have 1 factorial equals to 1 always. 2 factorial will be equal to 2 into 2 minus 1, that is 2 into 1, that is equal to 2. 3 factorial will be 3 into 3 minus 1 into 3 minus 2, that is equal to 3 into 2 into 1, that is 6. 4 factorial will be 4 into 4, 4 minus 1, 4 minus 2, 4 minus 3, that is equal to 4 into 3 into 2 into 1, that is equal to 24, and so on. The first property comes here is 0 factorial is always equal to 1. Second property says that factorial notation is defined only for whole numbers. The third property says that factorial of a negative integer is not defined. Now let's take an example, example number 4. If n plus 1 factorial equals to 12 into n minus 1 factorial, then find the value of n. The solution to this comes as n plus 1 factorial equals to 12 n minus 1 factorial, that is what given in the question. Now this comes as n plus 1 into n minus 1 factorial will be equal to 12 into n minus 1 factorial. So on both the sides, n minus 1 factorial gets cancelled and we are left with n into n plus 1, that is equal to 12. This implies that n square plus n minus 12 equals to 0. So that implies that n square plus 4n minus 3n minus 12 equals to 0. Now n into n plus 4 minus 3 into n plus 4 equals to 0. So this brings us to n minus 3 into n plus 4, that is equal to 0. So finally we have the values for n, that is equal to n equals to minus 4 and 3. Now n will be always 3 because negative n is not possible here. Permutation is an arrangement that can be made with a given number of distant objects by taking some or all of them. The word permutation stands for arrangement. The notation n permute r stands for permutation of n objects taking r at a time. That is, arrangements of r objects out of n objects when n is greater than 0, r is greater than equal to 0, and n is greater than equal to r. When we have n different objects, what is the permutation here? There is a theorem here. So what the theorem states here is number of permutations of n different objects taking r at a time is given as n permute r, which is equal to n factorial upon n minus 1 factorial. When n is greater than 0, r is greater than equal to 0, and n is greater than equal to r here. Now let's see the proof for this theorem. Let there be n objects in total. Therefore, there are n different ways to take out the first object. Now the number of ways to take out the second object is n minus 1. Since the second object is to be taken from any of the remaining n minus 1 object, thus the first two objects can be taken in n into n minus 1 ways. Now for each of these ways out of the remaining n minus 2 objects, there are n minus 2 number of ways to take out the third object. Thus the first three objects can be taken in n into n minus 1 into n minus 2 ways. Proceeding thus, the number of ways to take out the r objects out of n objects is given as n permute r, which is equal to n into n minus 1 into n minus 2, that is goes on and it goes to n minus r minus 1. This is equal to n into n minus 1 into n minus 2, that goes to n minus r plus 1. Now multiplying and dividing the right hand side by n minus r factorial, we get n permute r, which is equal to n into n minus 1 into n minus 2, that goes to n minus r plus 1 into n minus r factorial, the whole thing divided by n minus r factorial. That is equal to n factorial upon n minus 1 factorial. So therefore, we come to the conclusion that n permute r equals to n factorial upon n minus 1 factorial. Now we can also find the value for n permute n here. So that comes as n factorial upon n minus n factorial. So that is equal to n factorial upon 0 factorial. So that is equal to simply n factorial. So n permute n is equal to n factorial. Now let's take an example number 5 here. In how many ways 8 boys can stand in a row such that 4 particular boys are always together and never together? Let's see the solution for the first part. Let's take the 4 particular boys as one unit. It makes the total units to be 5 in spite of 8 now. These 5 units can be arranged in 5 permute 5 ways. In all these arrangements, the 4 particular boys will be always together. However, for each of the above arrangements, the 4 particular boys can be arranged among themselves in 4 permute 4 ways. Therefore, the required number of ways will be 5 permute 5 into 4 permute 4, that is equal to 5 factorial into 4 factorial, which is equal to 120 into 24, that is equal to 2880. Now the second part of the solution, the total number of permutation of 8 boys taken all at a time will be given by 8 permute 8, that is equal to 8 factorial, which is equal to 40320. Now the number of permutations when 4 particular boys are always together will be 2880. Therefore, the number of permutations when 4 particular boys are never together will be 40320 minus 2880. That gives you 37,440. Now let's see example number 6. In how many ways can 7 boys and 6 girls sit together such that they are alternatively seated? The solution to this is, there are 13 persons. For boys and girls to be alternatively seated, girls must occupy even places as shown. Now boys can be arranged among themselves in 7 permute 7 ways, and for each of these ways, girls can be arranged among themselves in 6 permute 6 ways. Therefore, the required number of ways will be 7 permute 7 into 6 permute 6, which is equal to 7 factorial into 6 factorial. This is equal to 5040 into 720. That gives you a figure of 3628800. So let's see now example number 7. How many 4-digit numbers can be formed out of 6 digits? 1, 2, 3, 4, 5 and 6 if no digit is repeated in any number. How many of these will be greater than 4000? The solution to this is, there are 6 given digits, that is 1, 2, 3, 4, 5, 6. Therefore, the number of ways to form a 4-digit number out of the given digits will be 6 permute 4. So that is equal to 6 factorial upon 2 factorial, which is equal to 720 divided by 2, that is equal to 360. A 4-digit number out of the given digits is greater than 4000 if it begins with 4, 5 or 6. Therefore, 1000 digit can be chosen in 3 ways here. The other 3 digits can be chosen out of the remaining 5 digits in 5 permute 3 ways. Therefore, the required numbers of 4 digits greater than 4000 is equal to 3 into 5 permute 3. So that is equal to 3 into 5 factorial divided by 2 factorial, which is equal to 3 into 60, which is equal to 180. There is a theorem for this. The number of permutations of n objects of which p objects are of one kind, q objects are of second kind, and all rest are different is given as n factorial divided by p factorial into q factorial. The above theorem can be further extended. If r objects are of the third kind, s objects are of the fourth kind, and so on, then the total number of permutation here is given will be n factorial divided by p factorial into q factorial into r factorial into s factorial, and so on. Now let's see the proof for this theorem. We know that the total number of permutations of n objects is n permute n or n factorial. Let us consider one of these permutations. In this permutation, P-like objects can be arranged among themselves in P factorial ways, and Q-like objects can arranged among themselves in Q factorial ways. The total number of different permutations will be n factorial upon P factorial into Q factorial. Now let's see an example number 8 here. Write all the permutations of the word examination in which vowels are together. Solution to this is, there are 6 vowels A, I, E and O in the given word. In order that these vowels occur together, let's treat them as one letter by keeping them together, or let's treat them as one unit. Thus the word now consists of 6 letters, namely X, M, N, T and A, I, E, O instead of 11 letters. Alright, among these 6 letters N occurs twice. Therefore the number of words formed will be 6 factorial divided by 2 factorial, which is equal to 360. However, the letters A, I, E, O can be arranged among themselves in the number of ways, which is equal to 6 factorial divided by 2 factorial into 2 factorial, which is equal to 180. Therefore, the total number of words having vowels together will be equal to 360 into 180. That gives a figure of 64,800. A circular permutation has no beginning or end, and so it is different from a linear permutation where there is a beginning or an end. In circular permutation, the position of an object with respect to its neighborhood is important. Therefore, in circular permutations, the position of any one of the objects is fixed and then the others are arranged among themselves. Therefore, circular permutations of n objects is equal to n minus 1 factorial. Now let's see example number 9 here. 30 employees are invited in an official meeting. In how many ways can they and a CEO of the company be seated at a circular table? In how many ways of these will 2 particular employees be seated on either side of the CEO? Now let's see the solution for this. Total number of persons here is 30 plus 1, that is equal to 31. Now 31 persons can be seated at a round table in number of ways, that is equal to 31 minus 1 factorial, that is equal to 30 factorial. Now let's treat the CEO and the 2 particular employees as one unit. So we have now 29 units in total. 29 units can be seated at a round table in the number of ways, that is given by 29 minus 1 factorial, that is equal to 28 factorial. But these 2 particular employees can be arranged on either side of the CEO in 2 factorial ways. Therefore, the total number of arrangements in which 2 particular employees can be seated on either side of the CEO is given by 28 factorial divided by 2 factorial ways. Each of the different groups or selections which can be made by taking some or all of a number of objects irrespective of the order is called a combination. Sometimes we are interested in arrangement but not selection. For example, out of the 3 objects, say A, B, C, 2 can be arranged in 6 ways, that is AB, BA, BC, CB, CA or AC. However, 2 out of the 3 can be selected in only 3 ways. That is, there will be only 3 combinations. That is called selection. So the 3 combinations will be AB, BC or CA. The notation N choose R stands for the combination or selection of R objects from N objects. N choose R makes sense only when N is greater than 0, R is greater than equal to 0 and N is greater than equal to R. In each of these selection of R objects from N objects, the R objects can be arranged among themselves in R factorial ways, that we know that. Now thus the number of combinations of N objects taken R at a time is given as N choose R, which is equal to N permute R divided by R factorial. Now N choose R therefore equals to N factorial upon R factorial into N minus R factorial. Now here is a theorem for combination. If some or all of n different objects are taken at a time, the number of combinations will be 2n minus 1. Let's see example number 10. There are 15 points in a plane. no three of which are collinear. Now find how many straight lines can be drawn. Second part of the question, how many triangles can be drawn? Now let's see the solution to the first part. A line can be drawn by joining any 2 points. Therefore, the number of lines drawn will be equal to number of ways in which 2 points can be selected from 15 points. So that is equal to 15 choose 2, which is equal to 15 factorial divided by 2 factorial into 13 factorial. So that gives us 15 into 14 into 13 factorial divided by 2 into 1 into 13 factorial, which is equal to 15 into 7, and that is equal to 105. Now let's see the second part of the solution. A triangle can be drawn by joining any 3 non-collinear points. Therefore, required number of triangles will be 15 choose 3, which is equal to 15 factorial divided by 3 factorial into 12 factorial, which gives us 15 into 14 into 13 into 12 factorial divided by 3 into 2 into 12 factorials, which is equal to 5 into 7 into 13, that is equal to 455. Let's see example number 11. There are 7 questions in part A and 6 questions in part B of a question paper. In how many ways can a student answer 7 questions if he has to choose at least 2 from each part? Let's see the solution. The student can choose 2 from part A and 5 from part B, or 3 from part A and 4 from part B, or 4 from part A and 3 from part B, or 5 from part A and 2 from part B. Therefore, the required number of ways in which a student can answer 7 questions if he has to choose at least 2 from each part will be 7 choose 2 into 6 choose 5 plus 7 choose 3 into 6 choose 4 plus 7 choose 4 into 6 choose 3 plus 7 choose 5 into 6 choose 2. So that is equal to 7 into 3 into 6 plus 7 into 5 into 3 into 5 plus 7 into 5 into 6 into 5 into 2 plus 7 into 3 into 3 into 5. That gives us the figures 126 plus 525 plus 2100 plus 525, and that is equal to 3276 ways. Now let's come to example number 12. There are 5 boys and 4 girls. In how many ways a team of 6 can be constituted, including at least 3 girls? Now let's see the solution. The selection of the team including at least 3 girls can be constituted either by selecting 3 girls and 3 boys, or by choosing 4 girls and 2 boys. Therefore, the required number of ways here will be 4 choose 3 into 5 choose 3 plus 4 choose 4 into 5 choose 2. So that is equal to 4 into 10 plus 1 into 10, which is equal to 40 plus 10, that equals to 50 ways. Let's come to example number 13. There are 12 points in a plane, of which 6 points are in a straight line. With the exception of these 6 points, no 3 points are collinear. Now, first part of the question says find the number of straight lines. Second part of the question says find the number of triangles. Let's see the solution to the first part. Since 2 points in a plane determine a straight line, number of straight lines obtained from 12 points will be 12 choose 2, which is equal to 12 factorial divided by 2 factorial into 10 factorial, which is equal to 12 into 11 into 10 factorial divided by 2 into 1 into 10 factorial, which is equal to 66. Now, number of straight lines obtained from 6 points is equal to 6 choose 2, which is equal to 6 factorial divided by 2 factorial into 4 factorial, which is equal to 6 into 5 into 4 factorial divided by 2 into 1 into 4 factorial, which is equal to 15. But these 6 points determine only one straight line. Therefore, the required number of straight lines will be 66 minus 15 plus 1, which is equal to 52. Now, the second part of the solution, 3 non-collinear points in a plane determine a triangle. We know that. Therefore, the number of triangles obtained by 12 points will be given by 12 choose 3, which is equal to 12 factorial divided by 3 factorial into 9 factorial, That is equal to 12 into 11 into 10 into 9 factorial divided by 3 into 2 into 9 factorial, which is equal to 220. But the number of triangles obtained by 6 points is given by 6 choose 3. So that is equal to 6 factorial divided by 3 factorial into 3 factorial, which is equal to 6 into 5 into 4 into 3 factorial divided by 3 into 2 into 3 factorial. That is equal to 20. But these 6 points being in the straight line determine no triangle. Therefore, the required number of triangles will be given by 220 minus 20, and that is equal to 200 triangles. Let's see in what cases we have some restricted combinations. The first one here comes as the number of combinations of n different things taken r at a time in which p particular things always occur. Here our job is to select any remaining r minus p things out of n minus p things. Since p particular things can always occur, so it can be done in n minus p choose r minus p ways. Therefore, the required number of ways will be here n minus p choose r minus p. Second one, the number of combination of n things taken r at a time in which p particular things never occur. Here our task is to select r things out of n minus p things, since p particular things never occur. So it can be done in n minus p choose r ways. Therefore, the required number of ways here will be n minus p choose r. Let's consider a case where p things are of one kind, q things are of second kind, r things are of third kind, and so on. When taken any number of things out of these at a time, the total number of combination of p plus q plus r plus so on things is given as p plus 1 into q plus 1 into r plus 1, that goes to minus 1. Now let's see the proof for this. In case of p similar things, any one of the p similar things can be taken or none of them can be taken. So there are p plus 1 ways in case of p similar things. Similarly, in case of q similar things, there are q plus 1 ways. And for r similar things, there are r plus 1 ways, and so on. Thus, the number of ways in which any of the things can be taken or not taken is given by p plus 1 into q plus 1 into r plus 1, and so on. But these ways also include the case when none of the things are taken. Therefore, the required number of ways will be p plus 1 into q plus 1 into r plus 1, so on till minus 1. Let's quickly see what we have learned in today's session. We have learned the fundamental principles of counting and their applications. In addition to this, the script has also solved several counting problems through the fundamental principles of counting and the concepts of permutations and combination. Also, the uses of factorial notations and application of different types of permutations and combination to solve various counting problems are also included in this script. So that is all for today. Hope you have understood how to solve various counting problems using the concepts of permutation and combination and the fundamental principles of counting, namely multiplication and addition principle that we have seen. We'll see you again discussing about our next topic now on matrices. Till then, take a good care and bye. Thank you.